first time. Oh, good. Oh, really? Good. Okay, it's time to start the first keynote talk. The speaker is the Dr. Yi Shen Yang from Taiwan, Taiwan National Taiwan University. We are very proud of having his keynote talks in the CMMR2023. And I heard that this is the first time in this year that he visited the go abroad. Okay, and I would like to introduce you about the Dr. Yang. And since February 2023, he joined the National Taiwan University. And before that, the 2019 to 2023 Taiwan AI Lab, and also the 2011 to 2023 this year. He belonged to the Academia Sinica. And he was also an associate editor of the IEEE Transactions on Affective Computing and the IEEE Transactions on Multimedia, both from 2016 to 2019. Okay, please start your talk.
Okay, hello everyone. My name is Yi Shen Yang. Thank you for being with us today, and it's my great honor to give a talk on my favorite topic in recent years. So I'll be talking about deep learning-based automatic music generation. So as we all know that there has been a great progress in deep learning-based music generation over the past few years. I still remember that 5 years ago, around 2018, people were still talking about MIDI music generation, right? And it's like all of a sudden, starting this year, we see large number of text-to-music audio generation models being proposed, right? To the point that even MIDI generation sounds like a bit out of fashion now. So people seem to care more about text-to-music generation. So let me give you a few examples. On the left-hand side, you see the MuseGAN model, which was proposed in AAA in 2018. And it is a model that can generate short clips of 4-bar MIDI music of 5 tracks. And it's unconditional generation with little user control. So this is the music that this model can generate. Pretty limited because it's fairly short and it's MIDI music, so it sounds mechanical. But it was considered as a state-of-the-art model at that time. Okay, and 5 years later, just a few months ago, we have the MusicGen model proposed by researchers from Facebook. And instead of generating MIDI music, it can generate musical audio. And it's not just short music, it's full-length musical audio with diverse instrumentation. And more importantly, such text-to-music models can text prompts, right? So it's much better user control. So for example, you can take a text prompt like this one, pop dance track with catchy melodies, tropical percussion, and upbeat rhythm, perfect for a pitch. This is the music that this model generates in response to this text input. Next example, the text input is a grand orchestra arrangement with sonorous percussion, and this is the music that this model generates. All right, as a the final example on the text input would be the classic reggae track with an electronic guitar solo, and this is the music that generated. Alright, so it's actually much better than before, right? So it's great improvement in just 5 years. So I think people 5 years ago won't believe that, we can have a model generate this kind of generate music of this kind of quality in just 5 years, right? So if you are a senior researcher with more than 10 years of research experience, 5 years is not a long period of time, right? So it feels like everything was done in a hurry. We don't have enough time yet to have a good understanding of a model, and then we are like pushed. Then there are new models. We are pushed to to keep track of the new model. So it becomes very hard. Everything moves so fast. It becomes very hard for us to keep track of the literature and to know what's going on. Right? I actually feel the same. So that's motivated me to prepare this talk to you, to connect the dots and to try to help you figure out what happened, okay, in the past 5 years. How come we can develop such a text-to-music model in such a short period of time? So according to my personal observation, there are at least 2 key technologies that enable text-to-music generation. The first one is language model for music. So language models include recurrent neural networks or transformers. They are good at modeling long-term dependency in the input data. So such models were initially applied to MIDI music generation because it's easier to tokenize MIDI music. Right? We just use the MIDI messages as a text token and use transformer and use a language model to model them. So research on this field helped us to go from generating a few bars of MIDI music to generating full-length MIDI music. And the second key technology is audio waveform encoder decoders, like VQVAE or audio codec models. Audio signals are by nature continuous data. So with this kind of audio waveform encoder decoders, we can tokenize audio files. It can be spectrograms or waveforms. Once we can tokenize audio files into discrete tokens, we can build a language model for musical audio over the audio tokens. And also we can learn the dependency between text tokens and audio tokens. So because of research on audio waveform encoder decoder, we are able to go from building a language model for MIDI music to building a language model for musical audio. Okay. So the objective of my talk today is give you guys a tutorial technical overview of the recent advances in deep generative models for automatic new generation. And my talk will be divided into 4 parts. First part, I will talk about data representations for symbolic and audio domain music. And then the second part, I will talk about the first key technology, that is language model for symbolic music. And the third part, I will talk about the second key technology, audio waveform encoder decoders. And finally, combining the two key technology, we are ready to talk about language models for musical audio. Okay? So let's begin with the first part. So this figure illustrates the connection, the relationship between the 3 core data representations of music. On the right-hand side, we see sheet music, which is in the visual domain. And on the left-hand side, we see audio representations, which are in the acoustic domain. In the middle, we have the symbolic representations, like those encoded by music XML files or MIDI files. So if you want to work on audio generation, likely you will use audio representations. If you want to work on symbolic domain generation, then you use the representation in the middle. So let's have a look at some of these data representations. First is sheet music. So as shown in the top right corner, a sheet music is a visual representation of the musical scores. Right? So it provides detailed information about the score itself. But because it's like an image, so it has been rarely modeled by deep generative models today. Okay? So the second one is a symbolic representation from music XML files. Music XML is a text-like representation of sheet music. Right? So you use a XML-like format to represent the sheet music. So we have text like note and /note. So such text can be easily tokenized and converted into discrete tokens. So it is possible to model them by transformers or other language models. So there is a model called the Score Transformer, published 2 years ago, that aims to model music XML data. So next one is the piano roll representation. It's a visual, image-like representation of MIDI files. It's also how people visualize MIDI files in DAWs. And it has been widely used by deep generative models over the past few years. So we have GAN-based model like MuseGAN or diffusion-based model like DiffRoll. There is also a library called PyPianoRoll that deals with the processing of piano rolls. And we also have the MIDI representation, which is a text-like representation of MIDI files. Right, so we can, the idea is to use native MIDI messages like node down and node off to represent the MIDI files. So a MIDI file becomes a sequence of such discrete tokens. So in this way, we can use language models like transformers to model such data. So there have been many transformer-based MIDI language models in the literature over the past few years, also some libraries to deal with such MIDI representations. So finally, we have the audio representation, which include the spectrograms or the waveforms. So both of them has been widely used in audio generation. All right, so let's take a look at the possible input and output in generative models for music. Right, so when the input is audio and the output is a symbolic music, then we are talking about a music transcription model. Right? And when the input is symbolic music and the output is an audio signal, then we are talking about music synthesizers. And you know, if the input and output are both audio, then there are many applications like have such input and output, like style transfer, denoising, source separation, super resolution, audio effect modeling, etc. So moving on, we have this this case where the input is like a random seed, or we are like generating from scratch, and the target is to generate music in a symbolic format. So this kind of systems are dealing with automatic music composition. Similarly, we have such model that aims to generate musical audio like unconditionally. And finally, we have text-to-music models where the input is user-provided text and the output is audio signals. Okay? So if you want to build a model of automatic music composition, likely you need a language model for symbolic music. And if you want to build a model for the last two cases, then you need a language model for musical audio. Alright, so let's move on and talk about language models for symbolic music. I will draw examples from existing work on MIDI domain music generation. So similarly, the past few years also seen great progress in MIDI music generation. On the left-hand side, you see Music VAE, which was published in 2018 by researchers from Google. It is a model that is capable of generating 16-bar monophonic melody. And the backbone of the model is a 4-layer recurrent neural networks. Let's have a lesson of the music that this model can generate. And on the right-hand side, you see the MuseNet model proposed by OpenAI researchers just 1 year after. And you use a much more complicated, sophisticated model. You use transformers, actually a 72-layer transformer decoder, also greater sequence length. And because of this, and because of such architectural differences, it is able to generate polyphonic compositions, and it's also much longer. Rather than 16 bars, you can generate 4-minute polyphonic compositions with up to 10 different instruments, like this one. Sorry. Okay. Like this one. Alright, so we know that transformer models are much powerful sequence models than recurrent neural networks. In recurrent neural networks, you use a single latent vector to represent the history. But in transformers, you use multiple latent vectors, right? Each corresponding to a time step in the history. So given these latent vectors, you have better access to what has happened in the past. So much better sequential information provided. Right? So nowadays, many people use transformers to build their language model for symbolic domain music generation. Then now we have a transformer model, then we need to talk about the data representation used to represent MIDI data. So if you are interested in building a language model for monophonic melody, then it's relatively more straightforward. Right? Because in melody, the ending of the note can be considered as just the beginning of the next note. Right? If you consider rest as another pitch. So for such a melody sequence, you can represent it as a sequence of pitch, duration, pitch, duration, pitch, duration tokens. Right? So the conversion is quite straightforward. So you can, given such a sequence of tokens, you can model a melody using transformers. But how about polyphonic piano score or performances where there are overlapping or concurrent notes sounding together? It's more complicated, right? Because you need to deal with the time flow. You need a way to represent time so that you can incorporate the case where there are temporarily overlapping notes. So actually in the literature, much research has been done to take care of the differences between text and symbolic domain music. I think there are at least 5 major differences between text and symbolic domain music. The first one is that in music, there are temporally overlapping events or musical notes. Right? This is not, this is absent for, in text. Right? There is no such case in text. So for MIDI generation, you need a way to represent the time flow. And second, a musical, to represent a note, we may need different tokens to represent different aspects of the note, like pitch, duration, instrument, and velocity, etc. So a musical note has to be modeled by multiple tokens or multiple attributes. And third, there are rich mid-level features like chord progression or grooving patterns in music. Such information might not be indicated on the musical score, but as human beings, we understand it. Right? As composers, they also have such mid-level features in their mind. So it might be important to take into account such mid-level features while we compute a tokenized representation for MIDI music. And fourth, music is rather long. Typically, if you want to represent multi-track or polyphonic music, you may need up to over 4,000 discrete tokens, right, for a single piece of music. So this can be considered as a very long text article. And finally, we know that music has a form, right? There is structures like verse-chorus structure. Music is not just randomly playing. There is some musical ideas or semantic contents that is supposed to be developed over time within that piece of music. So music generation is actually more like story generation. There must be a storyline, and there is supposed to be a structure within a piece of music. So we have taken into account all such differences between text and music while we are using our domain knowledge to build a transformer model or language model for MIDI music. So here are some issues here are some aspects that you may want to pay attention to if you want to build a language model for MIDI music, including the backbone neural sequence models and also the token design to better model the music in a better way, and also some model design to model the high-level structure in music. For example, let's consider piano MIDI generation. So for piano MIDI generation, there have been many approaches to represent the time flow in a piece of music. A common approach, known as the MIDI-like token representation, use the native MIDI messages like note on or note off and time shift to represent MIDI music. So note on indicates the beginning of a note, and note of indicate the ending of the note. Right. So this is a this is a usual way MIDI editors use to to visualize to process a MIDI file. But if you want to use such an input to a language model, then there will be some issues. Right. So first, there is no clear indication of the duration of each note. Right. So if you right, for the transformer, it had to have an idea of the duration of this note with MIDI number 6T. The model has to accumulate the value taken by the time shift tokens in between, right, to understand the duration of this note. Moreover, there is no indication of the bar lines, right, so the model may have a hard time learning the rhythmic structure of the song. So on the right-hand side is a token representation called REMI that is proposed to address such issues. So instead of using node on and node off, we replace the node off tokens by node duration tokens, right, to give the model a better idea, a direct idea of the length of each node. We also improve the way the time is represented by tokens using a combination of symbolic timing and absolute timing. We also include like core tokens to represent the mid-level features in music. Right. And model design is also important. So many people, when generating piano MIDI, many people use a one-shot approach, trying to generate piano music in just one single stage. But in ICAST this year, my group proposed a new model that decomposes the music generation process into two stages. So we first generate the lead sheet, right, the melody plus chord progression first as the outline, and then we generate the details of the piano performances. We found that this two-stage approach can better model the long-term structure in music because in lead sheet the number of tokens are less, and also it's easier to model the ABAA or this kind of song structure in the lead sheet stage. And then given the lead sheet, it would be easier to generate the piano performances accordingly, right? So I think this model kind of represents the state of the art in piano MIDI generation. All right, so if you are interested in piano MIDI generation, over the past few years, we have the pleasure to work on this field and propose a number of different models. So you can take a look if you are interested. And if you want to build your own MIDI transformer, here are some things that you want to consider. First is about the data. So you need to decide on whether you want to learn from MIDI transcribed from audio files, which include performance-related information, or you want to learn from MIDI scores. And also there are a great variety of different tasks in MIDI generation, such as MIDI melody generation, melody harmonization, piano performance generation, or multi-track generation, etc. So if you want to have an idea of the state-of-the-art models for each task, here is a GitHub repo that I maintain to help you keep track of what's going on. Right. So then, given the data and the task, you also need to choose a token representation. Personally, I would recommend the MIDI talk library, which implements a large number of existing MIDI token representations. And also, finally, as for backbone sequence models, there are also a number of models that you can choose. All right, so we have talked about the language models for MIDI music, but how about musical audio? Okay, so MIDI events are easier to be modeled by transformers because they are by nature discrete, right? They are discrete data. Audio signals are continuous, so it becomes less straightforward to apply language models to audio signals. I think that's why before 2022, most language models for music are for MIDI music rather than for musical audio. And without a language model, actually audio domain generative models in the past tend to work on short audio clips like single notes. Right? Okay. But things have changed lately. Okay, starting this year, we see a great number of language models for full-length musical audio. So what happened? Why this becomes possible? So to have an idea about this, we need to move on and talk about the second key technology, which is related to audio waveform encoder and decoders. So in what follows, I would like to introduce you to some breakthroughs in male vocoders, source separations, and audio codec models. Okay, all of them are related to audio waveform encoder decoders. So the first breakthrough is seen in audio source separation, in the field of audio source separation. So the task is about building a model which can take a waveform of audio nature as input and generate the waveforms of the source stems. So over the past few years, we also see great progress in audio source separation. In 5 years ago, WaveNet-based models can only achieve for vocal separation. WaveNet-based model can only obtain a signal to distortion ratio of around 3.5. But 5 years later, people can already improve the SDR by around 8 decibels. Right? This is a great improvement. And if you listen to the result of current source separation models, it's actually doing quite well. Right? The separated sources are very clean and there are not much distortions. So what we can learn from such source separation models is that in the literature, some people tried to build models, source separation models that take audio waveforms as input and take audio waveforms as a target output. So for such waveform to waveform generation models, we have gained many knowledge in dealing with such tasks. So I will recommend reading these two papers, the WaveUNet paper proposed in 2018 and the Demarcus V2 paper proposed 1 year after. Both of them deal with waveform to waveform domain source separation. But they have great difference in terms of the signal to distortion ratio that is obtained. So there's a 3 decibel differences. So in just 1 year. So if you want to understand what has happened, you can take a closer look and compare these two models. Okay. So the second breakthrough can be found in male vocoders. Right. So male vocoders are models that try to convert log-scale male spectrograms into audio waveforms. Right. And in the past, people tend to use a DSP-based method like the Griffin-Lin algorithm. But over the past few years, many people have proposed new models for neural male vocoders, and state-of-the-art models can provide much better result than the Griffin-Lin algorithm. So in terms of technology from advances in male vocoders, we learn better how to do upsamplings by neural networks, because male spectrograms are in lower dimension and waveforms are in much higher temporal dimension. So we have a better idea how to do upsampling by using modules like transpose convolution. And also, because the conversion from male spectrogram to waveforms requires a time frequency conversion, so we also have a better idea how to do this, using, for example, dilated convolutions. So from an application point of view, the advances of male vocoders also contribute to improvements in the quality or the audio quality of audio domain generation models. I still remember that in the past, people still consider like F0 spectral envelope and aperiodicity as the intermediate acoustic features in speech synthesis. But after 2019, suddenly people changed to male spectrograms as an intermediate acoustic features, because by working on male spectrograms, you can you have much richer information about the audio signal that you want to model, and after modeling the audio signal in the in the domain of male spectrograms, you can use a male vocoder to convert it back to audio waveforms. So such male vocoders have also been applied to signals beyond speech, so contributing to great improvement in audio quality across different audio generation problems. So these are male vocoders. And the third breakthrough has also to do with male vocoders, because you can notice that a large number of discriminators have been proposed and tested for male vocoders, such as multi-scale discriminator or multi-period discriminator. So such discriminators actually, basically male vocoders are for waveform generation, right? And such discriminators can provide much better losses than non-adversarial loss functions, such as mean square error. And I think the fourth breakthrough is related to audio waveform, VQVAE. Such models try to do neural discrete representation learning for continuous audio data. The goal is to recover audio signals from quantized or discrete representation of music, and then we want to recover the audio signals with high fidelity. So such approaches are mainly based on VQVAE or its friends, like RVQ or SQVAE. Alright, so combining what we have mentioned above, now we have the audio codec models, which represent actually the state-of-the-art approach for neural discrete representation learning for audio. So like we have the SoundStream model proposed by researchers in Google 2 years ago, and then in last year, researchers from Facebook proposed the encodec model, and there are many other new audio codecs proposed this year. So if we take a closer look at the model architecture of some of these audio codec models, like the SoundStream model, we realize that it has many elements. So the first element is, it is a model that, deal with audio waveforms at the input and at the output. So you actually need a waveform to waveform encoder and decoder. So this is related to breakthroughs number 1 and 2 that we just mentioned. And such audio codec models use a large number of discriminators, right, which were initially developed for male vocoders. So this is contributed by breakthrough number 3. And also, in between the encoder and decoder, people use vector quantization techniques to obtain a compressed or a quantized representation of the signal. So such vector quantization techniques are related to breakthrough number 4 mentioned earlier. So such audio codec models are not from nothing. It's actually standing on the shoulder of giants. Right? It's building on top of what we have achieved before. And interestingly, such models, you won't find any language models in such audio codec models, okay? Because an audio codec model is initially developed for audio compression. It's just for compression, rather than for generating something. So such audio codec models do not have a language model built in, okay? But the thing is that people should realize that audio codec models, because it obtains a discrete representation of musical waveforms. So actually it works nicely for building audio language models. Right? So starting this year, we see large number of text-to-music models which use such audio codec models to obtain a discrete representation of musical audio. So we can say that in the past, people over the past 3 or 4 years, people use male spectrograms as an intermediate acoustic features, and then use a male vocoder to convert male spectrograms into waveforms. But starting this year, likely more and more people will use audio codec as an intermediate acoustic features when building an audio generation model. All right, so let's talk about the last part. So I think we are ready now to talk about language models for musical audio. Okay? So such models are built on top of knowledge gained from building language models for symbolic music and as well as audio waveform encoder and decoders. So I think the first, one of the first famous language model for musical audio is the model, the jukebox model proposed by OpenAI 3 years ago. It's actually a hierarchical VQ-VAE applied to waveforms. So given a waveform, we use a hierarchy of 3 encoders to obtain a discrete representation of the audio waveform, okay, by using vector quantization. And then there is a decoder which is able to reconstruct your input audio waveform. And because the intermediate representation is discrete, so it will be possible to run a transformer over such VQ tokens to build a language model for musical audio. So this jukebox model is able to generate singing voices and backing track mixed together. And it is able to take conditions on lyrics, but not on general text descriptions like current text-to-music models. But the problem with the OpenAI jukebox model is that it's actually very expensive. Okay? So according to their paper, they require more than 500 V100 GPUs and also a very long training time. So this kind of compute is not available to most of us in the audience, I guess. So there has been little follow-up, at least before 2022. So last year, students from my group proposed a simplified version of jukebox. It's called Karasiner. So instead of applying hierarchical VQ-VAE on waveforms, we apply it on male spectrograms. Right? So male spectrograms are, in terms of the dimension, is much smaller than waveforms. So the idea is to apply VQ-VAE on male spectrograms to obtain discrete tokens for male spectrograms, and then finally we can use a male vocoder to obtain audio waveforms. So because we work on male spectrograms, this model only requires a training time of 4 days on a single consumer level GPUs. So it's much more affordable. And the interesting part of this model is that it is a model that generates singing voices given only the lyrics. Okay, so typically, in singing voice synthesis, you need the lyrics and also the melody as an input. But in this model, we try to build a model. In this work, we try to build a model that takes only lyrics as an input. So let me show you an example. Okay. Can you hear it? Let's try again. The text input is actually the abstract of our paper.
In this paper we propose nominal right now at mine. Called karaoke singer for a less studied singing voice in the systems. Names called free SPS, in which a prosody and money has been taken as laid inside of a machine.
Okay, so just one GPU is still possible to build a model like this.
In this paper we propose.
And actually, this is an unpublished result. Actually, the Karasiner can do something even more. So we have built an extended version of Karasiner where we just use the piano as the input to provide conditions for the singing voice generation model. So no lyrics and no melody are provided as input, just a piano music. So what we do is actually we take chroma features from the input piano and use that as a condition to generate the singing voice. So let's have a listen of this result. The volume is not big enough. All right, let's try again. Alright, because no lyrics are provided, so it's just like singing spontaneously, but it feels like it follows the music quite well. Okay, so let's. I have another example to share with you. It feels like it has good articulation, right? But we don't really understand what the model is singing. Okay, although this model is interesting, but it's actually not text to music, right? So what we do not provide the text description as the input. All right, so starting this year, lots of text to music models were proposed. Okay, so in text to music, the goal is to generate musical audio given arbitrary text input. Okay, so we have seen rapid progress this year. So this January, Google proposed the music LM model, and in May, ByteDance proposed the melody model, and 1 month after, we see Facebook propose music gen model, and there are many other new models. So such models use audio codec, okay, which apply VQVAE waveforms to obtain a discrete representation of musical audio, and then use transformers to model such sequences of audio tokens. So such models are still computationally expensive, but is at least cheaper than jukebox model by OpenAI. So and it generates music of high quality and with good diversity. So it's attracting. It also corresponds to the text input quite well. So such text to music models are attracting lots of attention. Okay, most models today only generate instrumental music, not vocals. And I also want to say that some of them do not use transformers at all. Some use diffusion-based models. Okay. In this slide, I want to show you a comparison between jukebox model, which was proposed 3 years ago, with two text-to-music models proposed this year. So in jukebox, to represent musical audio of 1 second, you need more than 3,000 acoustic tokens, okay, which is a lot. Right? This is a long sequence. If you want to generate music of, let's say, 10 or 30 seconds, then the sequence length is super long. Right? But because of the advances in audio codec models, text-to-music models like Music LM or Music Gen can use much shorter sequence of acoustic tokens to represent 1 second of musical audio. Right? So the number of acoustic tokens per second have reduced from over 7,000 to a few hundred tokens. Okay? So Music LM used the SoundStream model, which was proposed in 2021. Music Gen used encodec, which was proposed last year. And jukebox is not a text-to-music model, so there is no text encoders to deal with text tokens. And in text-to-music models like Music LM, it use contrastive learning-based joint text audio embedding model called MooLang to take care of the text tokens. And the Music Gen model use even more simplified and elegant architecture using pre-trained text encoders from natural language processing like T5 or FLAN T5. Alright, so you see that this, so we can, because of audio codec models, we can use less, fewer number of acoustic tokens, and now we have text tokens to deal with text input. So music LM, the music LM model proposed by Google researchers is very versatile. It can generate music corresponding to the text input. There is a story mode where you can use different text input to, to influence the music generated by in different parts of the piece of music. And also it's able to do text condition continuation of a given audio input. It is also able to do image to music generation. And the music gen model can generate music with even higher quality, and it generates stereo music. And it also provides more control. So now you can specify the melody of the music that you want to generate for music gen model. And it also has higher accessibility because researchers at Facebook, they share the model weights publicly. So you can actually do fine-tuning even if you don't have great computational power. You can do fine-tuning. Right? And in contrast, Music LM is not yet open source. So it's not available to us to play around. Okay? So what's next? We see large number of text-to-music models this year. So what's next? Everything is moving so fast. Can we have an idea of what is going to happen next? This slide shows you some latest development in this field. Right? Earlier this month or last month, actually people are providing more controls to such text-to-music models. So for example, now text-to-music models can take conditions on entire audio signal or take conditions on chords, drums, or piano rolls. It is also possible to use data from source separation to use to provide the model some audio tracks and ask the model to generate accompaniments. To generate other audio tracks for the same song. And also there have been attempts to build a unified model that can, to build a single model that can deal with all types of audio generation problems. This is actually a paper submitted to iClear next year. So it is a single model that can support up to 11 audio generation tasks, including text-to-music. Okay, so right. So what's next? Would you like to guess what people would be working on in the near future? What's next? It has been moving so fast. All right, here are some of my guesses. Okay, so according to my own educated guess, I think people will be working on creative use of text-to-music models, and also I think people will work on even better controllability, like the control net for text-to-music. Actually, today on Twitter, I just saw a new paper that built the control net for text-to-music. So this has already been done. The second one has already been done. And we can also foresee that people would work on more efficient fine-tuning of such giant text-to-music models. And also people might build smaller version of such text-to-music models to make them more affordable to every academic lab around the world, and also even on edge devices. And current text-to-music models do not generate scene voices, so for sure, people will be working on it, right? So people will build models that can generate scene voices in addition to the instrumental background. And we will also see that people will also work on text-to-music with song level structure, possibly learning from what people have done for language model of MIDI music. And the generation of music audio does not have to be done in one shot. So it is also possible that people build a model that generates MIDI first as an intermediate representation, right? It's like a two-stage generation. Given a text input, we generate MIDI as a skeleton first, as an outline of the music, And then given the media, we generate the musical audio. So I think such models we will see such models in the near future. And it is also interesting to decompose the text-to-music music production process into different stages. Like maybe we can control how the mixing is supposed to be done. Right. All right. So as a quick summary, so today I have mainly talked about two key technologies that enables text-to-music models, including language models for symbolic music, as well as audio waveform encoder-decoders that help us to convert continuous audio signals into discrete tokens. And there has been a blossom of generative models across different fields. Right? So we have ChatGPT, we have text-to-image models, we also have text-to-music models. So there are lots of open questions, of course, and also many future work to be done. Okay? So if you are interested in knowing more, I'm teaching a course on deep learning for music analysis and generation at National Taiwan University this semester. So I share my slides online, so just in case you are interested. Okay. Anyway, so that's what I want to share today. Many thanks for your attention.
Thanks so much. Any questions? Okay, first of all. Okay, good. Back. The man in black. Sorry. You're welcome. Thank you very much for a very interesting talk. When you said what's next, I was going to say, what about sustainability? You mentioned one of the earliest work they trained like a network of carbon dioxide spewing graphic cards computed for half a year, or was it 6 weeks, not 6 months? 6 weeks. All right. The AI has opened a lot of questions regarding sustainability in terms of social sustainability, economic sustainability, the austerity for people who are working in a creative sector, and also now with your talking, I wasn't aware of how much computational power these things demanded. So how do we, as a community, how do you think we should think about these things? Because this is fun, but at the same time, it's sustainable.
Yeah, I would say that's kind of beyond the scope of my talk today. I think my focus today is on the technical side. But it's true that such fancy text-to-music models are mainly developed by big companies. So it's very hard for us to catch up. And sustainability is a big issue. That's why many people are working on more efficient fine-tuning, right? And so, as academic people, I don't think that I would follow the trend and work on such big models. It's never possible, right? You don't have the resource to build such models. But instead, we can focus on some niche problems, or maybe we can build smaller version of such models, or do some more interesting fine-tuning. I think there are still lots of open questions for people in the academic.
I can just take the time to make a tip. Read Richard Slaughter's 4 articles about the oligarchs of San Francisco. Not San Francisco, but the Valley, Tech Valley. It's all about these big companies.
Okay, thanks.
Okay, thanks. Okay, next, the 2 rows from the back in green.
Thank you for your talk. I noticed that you didn't focus a lot on stable diffusion models, and I'm seeing that in the image generation space that's sort of taking over. And I'm just curious about your thoughts on how they compare to language models, or if that's sort of in the future.
Right. It's true. I mean, for strongly conditioned generation tasks like male vocoders, people are using diffusion models a lot. But I mean, diffusion models consider. I mean, we are yet to have a better understanding of the capability of diffusion models at modeling long sequences. Right? So images is just a fixed size matrix, and people use diffusion, in particular latent diffusion models, to work on latent representation of audio, bypassing the need of such audio codec models. Right? Because diffusion models can be applied to continuous data. Right? It doesn't require discrete input. But we are yet, I mean, we need more research to evaluate how good they are at evaluating long sequences. But I guess that's a trend, and people are working on it.
Including video generation, which does have a more temporal component.
Yeah, for sure. But personally, as a fan of video generation research, I think transformers still, because you quantize, you have a symbolized representation of each individual musical event. And with models like transformer, you can better understand the interconnection, the temporal dependency of such musical events. I don't know, I'm a supporter of transformer models. That's my personal opinion.
Thank you.
Okay, just the left side from you. Yes.
Yeah, to speak further on, I wanted to speak about what the aspect of control, when you were talking about the future perspectives. And I think conditioning is one of them. And then another one is this control of the mixing, right?
Yes.
So in a musical situation, for instance, the conditioning might be you could use your voice to mimic how you want the melody to sound or how you want the accompaniment to sound. And then you want to deal with these different aspects, right, as layers rather than a whole. But I think a question is then, because we're working in a lot of these cases with such a simple interface, right? Like you're talking about diffusion models, like stable audio. It's just text to music. But now we're going, if you're talking about conditioning, but especially if we talk about something that's multi-layered, now we're talking about a DAW or something like that, which people don't necessarily have access to. So I guess I'm wondering, have you thought about what is a paradigm for control where people could have that kind of meaning for control, but we're not, because it's such a paradigm shift to go into that. What do you think that might look like? And just to give a little small suggestion, I know in image generation, text to image, one of the things they're looking at is the organization like from CAD software, that to divide a scene into different objects and then you could shape the objects even using text. How do you think that would work for music?
Alright, so if we want to control how the mixing is done, what is missing now is a text description or related to the mixing process. Right? So existing models just use text descriptions like from the YouTube comments or playlist titles. Such text descriptions may not be related to how the mixing was done. Right? So the model won't have, the model doesn't have access to such information. So that's why it won't be able to learn such things. But I mean, if there is such a database with different types of text in different kind of musical labels, encompassing the composition related and performance related, acoustic sonification related, and as well as mixing related descriptions, perhaps, we don't know, big models perhaps is able to learn such connection between text and audio and decompose, these elements in the generation process. That's one possibility. On the other hand, perhaps we can do better, we can do some pre-processing or music processing to kind of recover, given an audio signal, for example, we can try to denormalize the audio effect that has been applied so that we have like, cleaned version versus a colored or processed version. And you can also apply source separation, many other kind of technique, or music transcription to have access to different layers in the piece of music, and you build text-to-music model for each of them. I don't know. I think the latter, we as an academic people, we prefer the latter approach. But people in big companies, maybe they just try the first one, and maybe the model is just able to do that. We don't know.
Okay, thank you. So unfortunately, we have run out of time. So I have to close this session. Thanks so much. Okay, next session will start 20 minutes later. Is it correct? Okay. So let's have a coffee time.
Turntable Rule Learning and Evaluation of Early 20th Century Music Styles. The speaker is Christopher Duyo. Please go ahead with your presentation.
Thank you very much for your time. Hi, I'm Christopher, and I'm from the Music and Culture Technology Lab from University. And today I will be presenting about, as you can see here in the title, it's it's a both objective and subjective evaluation about an interpretable rule learning of the early 20th century music styles. Okay, so before we are going further, is any one of you familiar with early 20th century music? Or raise your hand if you're familiar. Oh, good, quite a lot of. Okay, I hope all of you. Anyway, now I'm going to have a quick quiz about these three audios. So I have these three songs, and for each of the audio, I want you to guess if this is an early 20th century music or not. Okay? So for each of the audio. Okay, let's start for the first song. And anyway, this is just 5 or 6 seconds, so don't really worry about it. And it's not great here. So okay, so this is the first song. Okay, so raise your hand if you think this is an early 20th century music. Okay, quite a few, okay. Now let's go for the second song. Okay, raise your hand please. Oh, it's pretty obvious, okay, anyway. Now let's go for the third song. Okay. Raise your hand if you think this is an early 20th century music. Okay, anyway, here is the truth. All of them are early 20th century music. And my point why I actually give you all of these songs is that early 20th century music are very diverse. So for example, this first song is from Debussy, Reverie. Second song, maybe some of you may have guessed that this is actually Schoenberg. And the third song is actually a very famous Romanian folk dance by Bela Bartok. So, okay, so despite all of this, let's say, diversity of early 20th century music, in the music in information retrieval communities, is it still barely discussed? And some of the previous paper actually also mentioned that, okay, some of the label, most of them actually only consider the label of early 20th century music as modern. And I believe this is not particularly true, right? Considering that actually from the first, second, and the third song actually it's like very diverse and everything is early 20th century. So this has actually become our motivation to understand further about the early 20th century music, and it's become the object of my talk today. Okay, so moving on. So actually, as I told you before, now we are moving to the aim. So actually, our contribution of the paper is, they have three contributions of the paper. The first one is we propose a new data set of the early 20th century music in the symbolic format. And the second one, we try to investigate the uniqueness of the early 20th century music using some base rule learning approach. And the third one is the assessment of the generated rules in a subjective and objective manner. So maybe some of you may be wondering why we are using the rule-based technique. Because at the same time, previously you have seen a lot of sophisticated deep learning models. So it is actually related to the third aim of our research. This is for the assessment of the generated rule in a subjective and objective manner. Subjective here means that we want, let's say, fellow musicologists or music practitioners to be able to assess if the generated rule is actually make sense in terms of music theory, in terms of the stylistic styles or not. And this is also the reason why we are using the rule-based learning, because it's transparent and human can reason about the entire decision-making process of the models instead of black box models. And based on this, the second and the third aim, we will have this kind of, we aim to have new insights, and we aim to understand how the expert actually perceive the generated rules. So as I told you, we are actually having a new symbolic data set. I will actually explain a bit about the data set. So, okay, so we have, as you can see on the first table, we have the 4 different styles of early 20th century music data set, and it's because of the several things. First, early 20th century music actually consists of maybe more than 4 styles, but we are trying to take the common ones. And for the serialism here, I can explain you one by one. The serialism here, we have Schoenberg, Alvenberg, Anton Weber, and Hans Eisler, consists of 48 different samples. And for Impressionists, we have Debussy and Ravel. And Neoclassicism, we have Ravel, Hindemith, and Bartók. And Nationalism, we have Bartók, Janáček, and Dvořák. Most of the composers actually represent one particular stylus, except for Ravel, because Ravel early and late works actually quite different, and it can be considered in, let's say, the 2 distinctive styles. And also for, this is quite special for Béla Bartók. Because Bartók works, we personally handpick the Bartók works. And some of them, because it's quite diverse, and for example here, some of them consider as nationalism, and some of them consider as neoclassic. And there are also several Bartók music, for example, night music, that we don't include in the data set. And in addition, Arnold Schoenberg's previous pre-serialism works, we will not also include them. And okay, so there is also some limitation of the data set. First of all, we only limit it to the piano works. It is because we don't want we don't want any related problem. So compared to the instrumentation, so that's why we decided to just use the homogeneous piano works. And the second one is actually we only include the first 2 measures, which is approximately 1 page. And the third one, the most important one, we only consider the public domain. Because, okay, so as much as I want to add Stravinsky inside this data set, unfortunately, by the time I'm doing this data set, it was not in the public domain yet. And lastly, this is how I actually do the data set. So first of all, I gathered all of the required scores from the Petrucci Music Library. Maybe some of you musicians are very familiar with it. And afterward, we convert everything to music XML. After the data set of music XML is done, we extract node events, which consists of several things, including the beats and pitch and etc. After we get all of the data set, now let's go to the data representation. So for the extracted node events that we have, we create some fundamental pitch and intervals elements. So for example here, let's go to the first part. The pitch is the range of pitch among all of notes in a piece. So it means it is a distinct. We find the highest notes and the lowest notes, and actually find the range in a MIDI number. And the second one is the mean of the pitch distributions. And the third one is the standard deviation of the pitch distributions. Continue, we also have the vertical intervals. It's actually the intervals between notes in the same time steps. In our paper, we actually denote this as the V interval names. And for the horizontal intervals, it is also intervals of neighboring nodes in the different time steps. So for example, given 2 time steps, I can explain to you later in the next slides. Anyway, this is H interval names. And actually, we also extend the horizontal intervals. to a horizontal interval with n skips, which is actually inspired by the n skip gram from natural language processing. So we actually interval, it's actually quite the same interval of neighboring nodes, but we are considering different time skip. So we also denote this in the paper as H interval name n skips. Now moving on, I will give you a little bit of example of this one. So yeah, as you can see here, this blue one is actually a vertical intervals, which is actually in the same time step, you consider all of the combination of the nodes and you find the intervals. So for example here, I give you one example. This is A sharp to C sharp, so this is a minor 3. It's denoted as V as a vertical intervals and minor 3. And the second, the green one, is actually the one with the skip gram. So since we are using one skip, so we actually do not really use the second time step and go directly to the third time step. So as you can see there, it is denoted as HM3 with one skip. Lastly, we also has the standard H horizontal interval M2, major 2, and it is actually, it is a neighboring nodes. And for your reference, we only consider the maximum skip of 2. And after we get all of the distribution, all of that, we actually make it a distribution of the interval occurrence, and we normalize it with min-max normalization, and it resulted in the 13-dimensional filter factors. So, considering the vertical intervals, horizontal interval with one skip, horizontal intervals with 2 skips, so we have a total of 52, plus the pitch range, standard deviation, and also the mean. So we have 55-dimensional feature factors. So moving on, now we are going to the models. So since this is we focus on the rule-based learning, right? So we actually have 3 different kinds of rule representations. For example, the first one for the rule, we have rule 3, rule list, and the rule set. So for rule 3, we are utilizing very famous decision tree classifiers, and this is the parameters that we are using, and this is the example of the rule 3. But I believe that most of you may have seen this or at least used this before. And now let's move to the rule list. So instead of the 3 models, what we are doing as a rule list is like some kind of nested if and else statements. So yeah, so the rule list that we are using is a minimum description length rule list with these parameters. And last but not least, there is a rule set, which is we are using a scope rules. And instead of the if and else statements or tree, we are using some kind of tabular data. Now moving on. So yeah, for the training, I will be pretty quick for this one. So we create data augmentation, pitch shifting, take some of the samples to avoid a very imbalanced data sets, and we change it with 80 to 20 training and testing, and 5-fold cross validations. And after that, we conduct objective and subjective evaluations. Now for the objective evaluation result, based on our 3 algorithms, we can see that actually rule set perform the best, and following the rule 3 and the rules list. And yeah, and this is the average result from 5-fold cross-fold validations. Now let's move to the subjective evaluations. So so for this one, we have the aim and the questions. We have 2 different kinds. The first one is visualization to see which rules actually matters the most, which rules that musicology is more preferred. And the second one is the content test that's actually evaluate the rules itself. And this is actually the result. So actually in terms of visualization, rule 3 is the best, but for the content test, rule set is actually the best. And it's actually pretty similar with our objective evaluations. Last but not least, we can actually have the case study of the rule set here. So this is pretty interesting because actually some of the rules actually, and we actually randomly select 4 different musical excerpts from our data set. And as you can see here, actually some of the rules actually fit to the respective styles. For example, Impressionism usually have wide pitch range or wide register, and also there is also weak rules that actually, because the threshold is very small, And also there is also some kind of unusual rules. Since the time is up, so this is the conclusion. And thank you very much. Please let me know if there's any question. Thank you.
Or comments?
I have a question.
Please.
Okay. Thank you for a great, interesting talk. So my question, the first one is, you're already saying that you're focusing on 20th century music, early 20th century, and you're kind of confident, but the problem is that you actually will have to do the same thing for music from other centuries to actually compare. As if talking about 20th century as being unique is valid, right? If you actually have similar clusters or similar statistics from other eras, then you're saying that you're studying 20th century and trying to find how to classify them. I'm not sure how valid that could be. And secondly, for instance, you've omitted the Rachmaninoff, who is definitely one of the most well-known early 20th century musician, who has a reputation of being the heir to the classical tradition. So people say his music is closer to the classical era than 20th century. Then if you omit that, then what do you achieve by omitting one of the major composers?
Thank you very much for the questions. Oh yeah, yeah. So since okay, so let me actually answer the first question. So it is very interesting questions. So it is actually I can say that some of the early 20th century music has a very different type of let's say the way of compositions. But I believe that in our from our discussion with the second supervisor, which is also a composers, actually we can still find something on the fundamental theories. So for example, for the note distribution, pitch distribution, and also interval distributions. And there is some interesting find that actually doesn't really connect with the music theory. For example, for the serialisms, since they have the utilization of tone drops, right? So I assume that actually the pitch distribution would be similar to one another. But from our finding, it's not actually that way. So we have quite a different result compared to the let's say well-known music theory about the pitch tone drops. Okay, and can you please repeat this question?
Yeah, second question. So you just said that there's something fundamentally different about the early 20th century music, right?
Yeah.
But Rachmaninoff actually is one of the most major composers of the era. He is omitted. And fundamentally, he is known to be closer to the older generation's music. So if you take out what does not fit your understanding of the fundamentals, then explain that you're actually taking out something that would negate your arguments and saying it is fundamentally different because we've chosen something that actually adheres to my evaluation.
Okay, got it. Okay. So another interesting question, of course. Yeah. Okay, so in our understandings, we also because if Rachmaninoff, as you mentioned, is more closer to the late Romantic instead of the early 20th century, it's actually the style we are not considering. So that's why we do not take a lot of, because I believe that there are a lot of early 20th century music that's actually closer to not only Rachmaninoff, but...
So was it a conscious choice to take out Rachmaninoff in your data?
Okay, so basically, right, first we only limit the four styles, and the second one is that when creating the data set, we create by our own with the human labor. So actually, one of these human labor, lack of human labor, actually one of them that we actually just focus on the four styles. But it's actually it's very interesting take, and I will consider it in the future. Thank you very much.
Okay, time is up, so please continue discussion on Slack. So let's move on. Thank you very much. Let's move on to the next presentation. The next presentation is Third Empirical Analysis for Stylistic Expression in Piano Performance. The speaker is Ms. Yu Wen Fang. Please go ahead.
Hi,
Hi, good afternoon. I'm Yifeng Huang from Academia Sinica 1. The topic I'm going to present today is toward empirical analysis for stylistic expression in piano performance. Why do we need to analyze performance style at all? If we search for a specific piece of music on streaming service, for example, Spotify, there may be dozens or even hundreds of different versions for the same piece of music. For instance, when we listen to this version of Mozart Piano Sonata, which is played by Mitsuko Uchida. And this will sound quite different from this second version. Do you want to guess who is playing? It's very cool. Yeah. Very unique style. The question is then, how can we describe the actual differences between these two versions in a very specific way? The formation of performing styles is a complex interaction between many different factors, including the compositional factors in the music pieces, and the musician's personal interpretation or expressive styles. Jocelyn has summarized 5 different factors affecting the formation of music performance, including the generative rules, the emotional expression, rhythm variations, motion principles, and also stylistic unexpectedness. In this context, expressive variations in music performance are considered as the means to communicate musical ideas. And several previous works examine music performance in a systematic way using MIR techniques or computational models. To systematically examine music performing styles, the aims of this paper are therefore, the first, to collect a piano performance dataset with controlled experimental design. Second, to identify key factors in musical expression using statistic methods. And third, to provide empirical observations of performance style using time series analysis. For data collection, we recruit a pianist to play 3 classical music by Bach, Mozart, and Beethoven. And each pianist played the same piece of music repeatedly for 3 times for comparison. The performance is recorded in both MIDI and audio formats, and the MIDI file is used to align the performance with the music scores in the following stage. The data is collected in a motion capture lab, in which musicians' body motion is also recorded by a 3D motion capture system, which we will analyze in another work. After the recording sessions, audio recordings are aligned with music scores using an HMM model in which we can locate the onset of each note in the performance. We then extract bar-level expressive features, including the tempo, which is defined as the average BPM per bar, and the dynamics, which is the maximum volume on the note attack per bar. We then use statistical methods to examine the influence from different factors, including the composition factor and the musician factor. Following the standard procedure of statistics, we perform the normality and homogeneity
test first. We then perform one-way ANOVA for 3 different music pieces and 8 different pianists. If the data distribution violates the assumption of normality or homogeneity in the first step, we choose to run the non-parametric test instead. Corrections is applied in the post-hoc test for multiple group comparison. For the tempo variation, the statistic test produced significant difference between 3 different compositions. Specifically, Bach's music has lower mean compared to other 2 music pieces, and Beethoven has more tempo variations. In general, there are significant difference between different pianists' tempo variation, but in the post-hoc analysis, the difference between some pianists are not very obvious. For the dynamic variation, there are significant difference between 3 music pieces. Specifically, Bach's music has softer dynamic level compared to other 2 music pieces. There are significant differences between different pianists' tempo variation, but the difference between some pianists are not very obvious in the post-hoc analysis. In the second analysis, we examine the interaction between different compositional and expressive elements for 104 different groups. For expressive elements, we examine the tempo and the dynamic per bar. For compositional elements, we look at the section boundary, the phrase boundary, the section position, which is the first, the middle, or the last 1/3 of the section, as well as the phrase position and also the harmony types. We choose those elements to look at since previous studies have shown that phrase, section, and harmony are important elements to affect musical expression. We run the normality and homogeneity test first. Then we perform t-test for 2 group comparison and one-way ANOVA for 3 group comparison. Or if the data violates the normality or homogeneity, we choose their non-parametric counterparts. This graph shows the mean, the standard deviation, and the significance level of statistic test. For the tempo variation, as we expect, pianists tend to slow down at section or phrase boundaries, and also the harmony of tonic or dominant chords, which sometimes coincide with cadence. But different expressive styles do emerge when pianists perform different music pieces. When playing Mozart, musicians tend to slow down, then speed up during the section. Whereas when playing Beethoven, they tend to play ritardando toward the end of the section. For the dynamic variation, pianists tend to play in softer dynamics at phrase boundaries. But musicians use different strategies to express section structure. When playing Mozart, they tend to perform crescendo and then decrescendo during the section. Whereas they play decrescendo when performing Beethoven. In the following analysis, we examine that how musicians use different manners to express 3 different music pieces. This is the tempo, dynamics, phrase, and harmony analysis for Bach's music, which sounds like this. Of music. And musicians play in steady tempo with only a very obvious ritardando at the final cadence. But we do observe that musicians use the dynamic variations to highlight phrase structure, in which they perform crescendo then decrescendo for each phrase. And for the harmony structure, they use softer dynamics to express the return of tonic, which is the release of harmonic tension. There are three different themes in Mozart's work. Theme A. And lots of chords in theme B. And 16 notes in theme C. Different from the smooth tempo curve in Bach, the tempo variations in Mozart reflect both the phrase and section structures, in which musicians tend to slow down at boundaries. For the dynamics, this piece shows contrast dynamic level between theme B and other sections, owing to the chords played by the two hands simultaneously in theme B. And the low point in both tempo and dynamic curves also corresponds to the half cadence or the full cadence in the harmony. For the last piece of music, Beethoven's piano sonata has two different themes. Theme 1. And theme 2. It is very evident that in this piece of music, musicians emphasize the high-level section rather than local phrase structure, in which they use very obvious ritardando to emphasize the end of each section, whereas the phrase structure is not very obvious in the tempo curve. They also use a wide range of crescendo and decrescendo pattern in each section. Yet the local low points in tempo and dynamic curves also reflect the phrase and harmony cadence in a small range. To summarize, we often consider performing style as an ambiguous concept and describe those styles in a very subjective manner. But in this study, we demonstrate an objective and empirical way to describe specific performing styles, specifically using statistical methods and time series analysis. Overall, we observe that musicians use tempo variations to specify phrase, section, and harmonic tension. Yet they emphasize high-level section boundaries when playing Beethoven, whereas they focus on local phrase structure when playing Mozart. The tempo variations are not very obvious in Bach's music. For dynamics, musicians use dynamic changes to signify phrase, section, and harmonic tension. They focus on section structure when playing Beethoven. While playing Mozart, they use a unique strategy that is a contrast dynamic levels to distinguish different sections, which is not shown in other music pieces. The expression of section structure is not very obvious in Bach's work. Of course, these analyses are limited to the selection of repertoire. Different pieces of music may show different characters, and different musicians may also tend to use various ways to express the same piece of music. This concludes my talk today, and thanks for your attention.
questions or comments? Please.
Yes, I noticed one of the, first of all, really very interesting analysis. I noticed that when you had the control groups, when you had the statistics about the methodology, that you had a breakdown of gender. And did you do any analysis in that regard?
Do you mean the second analysis with 104 groups?
Yeah.
This one?
I mean, wait a second. Wait, if I look at my phone, I can see the slide. It was when, let me go back. It was when you...
Or this one?
Before that, I think.
Before this? Those are...
That's it.
This
Next one.
This
Well, oh no, it was before that. Sorry. There you go.
Okay.
There you go. Yeah, about your pianists. So what I was wondering is, did you do any breakdown among those pianists of looking at the data, if there was a differentiation of the data according to the gender?
Do you mean that is there any difference when different pianists play the same piece of music?
Yeah, in other words, this final data that you had,
Yeah.
I was wondering if you also did some kind of cross section of, like, can I see the last slide?
Yeah, but the result is shown in this one.
Were you okay? That's right. But did you have some differentiation between gender, basically?
Yes, because we do analyze two different factors, and this one is a difference between different pianists. Yeah. So we compare if there are any significant difference between different compositions, and those are the difference between pianists. And some pianists do have difference, but those pairs listed there has no significant differences. So it really depends on the pianist.
Okay.
Some pianists are different, but some of them have no significant difference according to statistics. And we do that on the tempo and the dynamic. Yeah.
Okay, so in other words, difference was pretty much evenly distributed among the pianists, and you didn't see any grouping of difference according to gender.
Some of them are different, but
Yeah.
some of them are pretty much similar.
Okay.
Yeah, it really depends on the pianist according to the analysis results.
Okay.
Thank you so much.
One question.
Hello, thank you for this talk. My question is, were there any instructions given to the pianists, like trying to be historically accurate, for example?
And now we just let them play in their own way. But we do provide those music scores for them in advance so that they can practice very well. And we do record each pianist 3 times, just repeatedly. But we do not compare the difference between their 3 trials in this paper. Yeah.
Okay, and do you know if they're all trained at the same conservatory, for example?
Oh yeah, they are all from the music department in the university. So yeah, I think there are some of their basic information here. So they are very well trained pianists, yeah, because they are all majored in music in the university. So they have trained for more than 14 years. Yeah.
Okay, thank you.
Thank you very much. Okay, so the time is up, so we will conclude this presentation. Thank you very much. The last presentation in this session is Sangeet, XML-based open dataset for research in Hindustani Sangeet. The speaker is Mr. Chandra Misra.
don't you have a laptop?
Yes,
Really?
I don't have a laptop.
Really? Okay, so do you have a file? Do you have a file?
Google Cloud.
Okay.
I didn't bring my laptop.
So it's a Japanese version. So and then so you have to you have to access Google Drive or something like that.
Right, Google Drive. So good afternoon everyone. The title of my paper is Sangeet, an XML based open dataset for research in Hindustani Sangeet. So before starting the presentation, I would like to thank the undergraduate students of School of Computer Science and Engineering, Exam University, for helping create the dataset. So having access to free, well-maintained databases of music is a crucial resource for researchers. In the case of Indian classical music, this is also true, since it has been shown to be important for high-quality research in music information retrieval and musicological analysis using machine learning and deep learning. So several high-quality datasets for research in music information retrieval and computational musicology can be found in the published literature. One of the most well-known and maintained dataset is Saraga, which is one of the many datasets created under CompuComp Music project from University of Pampufabra. It is a high-quality open data collection for Indian art music and Hindustani and Carnatic music consisting of audio recordings and corresponding time-aligned melody rhythm and structural annotations for the complete duration of the recordings. Although audio recording based music corpora are essential in certain types of music applications, studies of existing literature reveal a dearth of substantial research related to the varied domains of sound and music computing, especially in the design and development of interfaces for expressing indie music on an electronic medium. So one of the domains that interest us is the creation of an indie music environment through the transcription and rendering of an indie music piece using indie notation systems and indie language script. The ability to compose music electronically entirely in an Indian music environment necessitates the emergence of research in different domains in sound and music computing. This requires a musicological analysis of the grammar and structure of the music sheets presently in the use, and the consequent development of musical fonts and rendering engines. Needless to say, such endeavors would motivate the research community to create models for Indic music notation systems and their language bases, and provide ample opportunities to work in building interfaces for music expressions on an electronic medium. So one of the most authentic sources of Hindustani Sangeet is the compositions published in the book Hindustani Sangeet Paddhati Kramik Pustak Malika, which comprises of approximately 1900 compositions belonging to North Indian classical music penned by Pandit Vishnu Narayan Bhatkande. In order to reach a greater number of music students and scholars, the first volume of Kramik Pustak Malika has been translated to Hindi in 1953 by prominent music scholar Dr. Lakshmi Narayan Garg. Now this paper introduces Sangeet, arguably the first XML-based music corpora that try to capture comprehensive musical information contained in these rich music sources to apply in various music applications like music transcription, visualization, music information retrieval, computational musicology, etc. We begin the preparation of the dataset with the second volume of Kramik Pustak Malika book series, and our objective is to store compositions of different genres in a carefully crafted XML database to preserve comprehensive musical information in a single format. The dataset created in the current work has been taken from the Hindi translation of the second volume of the series. The second volume of the book series contains a total of 319 compositions belonging to 10 different rags. The present work takes these written compositions as a source of musical information to create the database for Hindustani Sangeet to be used in various applications. So we have taken 116 compositions of the three highest frequent rags, that is Rag Bhairav, Todi and Purvi, respectively, from the entire collection. Eventually the entire collection of compositions from all 6 volumes will be preserved in the dataset for application related to MIR visualization tasks. The dataset consists of a number of XML documents that is equal to the number of compositions in the dataset. That is, each XML document represents a single composition of the dataset. The XML documents are equipped with meaningful tags to store all the necessary musical information for the compositions. The format of the XML files is validated against a schema definition document so that the format of the dataset or compositions are preserved. The schema definition document is an XML schema definition file against which each XML document is checked and validated for legal elements and attributes. The XSD consists of 4 parts, namely info, tal, rag and sheet responsible for storing metadata, rhythmic, melodic, structural and notational information in the XML files. These are some of the examples of how we have stored the various modules of the compositions in XML files. This is the structural part. Now I am going to demonstrate 3 applications that is relevant to the dataset. The first application where we can appreciate the power of XML as a means of build musical dataset. Now, one of the primary applications of any music dataset is to visualize it or render it using a notation system in which it is preserved. We have encountered several difficulties in visualizing the composition in the Bhatkande notation system, since there is no standard font system for rendering Bhatkande music symbols in any language script. The closest rendition we have found is Om Swaralipi, system, which is a compact version of the Vatkande notation system and easy to use. In order to visualize in HTML format, the system provides the necessary styling information to render it in Devanagari script. Therefore, the pre-processing step for the application is a converter that takes an XML file as a standalone composition and transforms it into an equivalent HTML with the Om Swaralipi rendition of the score. The second application is where we can appreciate the power of XML as a means to build the music dataset. For the present application, we have used two tools, namely XPath and XQuery. XPath, the XML path language, uses path expressions to parse through the elements and attributes of an XML document and select node elements to extract the contents inside it. This language is also used in another query language, XQuery, to query an XML database and retrieve required information from it, much like the SQL that does the same on the relational database. The pre-processing stage for this application is to create an XML database created from the XML documents. We have used Basics database engine to create the database from our dataset and XQuery to efficiently and easily perform complex queries and retrieve information from it, and therefore can be extremely useful for data-intensive complex web applications. The last application refers to the musicological analysis of various musical components present in Hindustani Sangeet. It covers statistical and structural analysis, data mining and inference using machine learning and deep learning techniques. As an example of the application, we apply machine learning techniques on the dataset for the task of RAG prediction. The pre-processing step for RAG prediction is to convert the XML dataset into a tabular data frame containing a number of features and a target variable. For RAG prediction, we take features as the frequencies of individual notes and the corresponding RAG as a target variable for any composition. Instead of taking the note frequency distribution of 36 notes for a composition spanning across 3 octaves, we merge the notes to obtain the frequency distribution of 12 notes. Since the positions of the notes of the Arohan and Avarohan, that means ascending and descending pattern of any particular composition in different octaves do not affect the RAG of the composition, we map corresponding notes of 3 octaves and make a sum of frequencies of corresponding notes to obtain 12 note frequency distribution. The table shows the measure of performance of different machine learning techniques for RAG prediction for our dataset. We have transformed our dataset into a 3-class classification problem by taking the 3 most frequent RAGs, that is Bhairab, Tori and Purbi, and applied the different classification models to generate the accuracy scores. Since each classifier examined shows high accuracy score, the dataset can be considered as a robust dataset for RAG classification. Table shows a k nearest neighbor with k is equal to 3, and decision tree classifier gives better accuracy scores than the logistic regression model. Thank you.
I am interested in how kind of music the North Indian classical music is.
Sorry again?
I am interested in how kind of music the North Indian classical music is.
There are mainly two prominent classical music in India.
Okay.
One is North Indian classical music, which is also called Hindustani Sangeet, and South Indian classical music, which is also called Carnatic Sangeet.
Okay.
And apart from that, there are 1 or 2 prominent regional music, which has their own singing style, melody style, and different notation system.
Can you see that?
No.
Okay, so do you have any questions or comments?
So could you show the notation with the Devanagari script? So is this Sarigama Padani?
Yes.
So one thing is, so is this notated with your software?
Yes.
So it'd be useful, can you do like Latin transliteration?
Then we need a different font.
But you can use Unicode, for example.
So this is not Unicode.
But
so the symbols of Indian notations for North Indian classical music has not been encoded in Unicode. So that is the problem.
But there's, well, yeah, so you have like dots above or an octave above. What are the dots?
So there are 3 octaves.
So it means octave higher, right?
Yeah, so.
But it's a composite symbol.
Yeah, but so whatever you are seeing, the bar below any note, a bar, horizontal bar below note.
Rhythm?
No, that is in lower octave.
Okay, lower octave?
Yes.
And the dot is octave higher?
No, that is a sharp.
Okay. But these are like composite symbols. So
yeah.
The core is just Devanagari.
So each one is a note.
But the core is Devanagari.
Yeah. So notation system largely depends on the language you are using. So if you are using a different language, the notation system changes.
But this script, I mean this
script is Devanagari.
The font is, these are symbols with the dots included in the font?
Dot included.
Okay.
Yes.
But it'd be easier maybe to have a more graphical representation, so you can have the core character, which you can change to different scripts.
Oh, okay, yeah.
So use the same graphical symbols, but the different scripts.
Yes, once we encode the symbols in Unicode, then we can do that easily.
Yes, so that's very interesting.
Yes.
Well, one more question
Yeah.
is in Indian music, and also in Asian music in general, it's traditional to only work from memory. So these, but these were written down, so it's kind of like a 20th century movement.
No, actually, there is a lot of scope of improvisation in Indian music. So they don't actually see the music sheet while performing. They just memorize it and then they perform.
Well, and then they improvise on it.
Yes, but there are applications. Say, for example, I am going to archive very primitive Indian music sheets. Then what is how I can do that? So for that we need this kind of systems.
So would these be performed as written, or they're like, so in house usually you play the written and then you improvise after?
Yes, that is depend on the singer and the performer.
Okay, thanks.
Thank you.
Okay, we have just a little bit of time left. Please.
Hi, thank you for your presentation.
Thanks.
Just to follow up on that question, because Hindustani classical music has different gharanas and styles, and in more, I will not say realistic, but in more, a lot more applications, the performance analysis is very important. And this is where the stylistic difference comes into play more than the actual set of ragas that are being sung at the piece. So do you think that your work can be extended to such kind of applications, and how would you plan to do so?
Unless and until more up-to-date notation system is coming, you cannot do such kind of things. Say for example, whatever you said for different gharanas, but the notation system remains the same.
But you might be having some sort of metadata in terms of what kind of improvisation there might be from still specific styles or specific prominent singers.
Yes. So in our standard that we have done in the past, as a Sangeet XML, the standard we have done, there is a provision of giving different information for the melody. So if you can add, so the author can add different kind of things in the melody part, and I think that could be rich here. Yes.
I see. Thank you so much.
Thank you. Time is up, so we will conclude this presentation. Thank you very much. All presentations in this session have been completed. Finally, I would like to applaud all the speakers and participants who took into the discussion. Thank you very much.
Thank you for participating in the conference today. So I have a few announcements. One is, if your today's poster presenter removes your poster